I was a bit concerned early on. You all seemed so quiet, but you seem to have livened up now, and now I'm more worried you're going to be more too lively. I'm going to try to keep you under control now. So welcome to the Drives theme talk. Of course, in Drives, we're right at the opposite extreme to what you were getting from Phil, where Phil was talking about devices. Now we're looking at much more an integrated system. In terms of who we are, I've put everybody down here that I could think of. I hope I haven't missed too many people out. But you can see we have people from Bristol, Manchester, Newcastle, Nottingham and Sheffield. The people I put in bold are the PIs at each of the principal investigators from each of the universities. Within this we have research staff and we have a good number of postgraduates as well. So when you look at that in total, we've actually got quite a big team, many of which are funded externally, particularly the PhD students. But it's given us quite good gearing in terms of how we've managed to get people for the amount of money we needed. What I would say, I suppose what's probably been most, if you might, almost surprising, I shouldn't say that, is how well we've all worked together. It's been really good collaboration between everyone, and we've worked very well as a team. And it's been great to see us having some really detailed discussions on things where we normally competing with each other and working together to come up with new ideas. The one area where we haven't worked together very well was in preparing this presentation. What happened is I said to everybody, could you give me a few slides? And I gave them the pro forma and said to everyone, half a dozen slides or so on what you're doing. And then everybody thought, well, we're doing so much. What we'll do, we've got 30 slides worth. So what everybody did is they gave me 30 slides worth of material and just compressed it into 4 or 5 slides. And the text was so small and it was all so dense and there was so much material. You'd have been here for 3 days and you would have all needed binoculars to see what was there. So I apologize to all my co-investigators. I have sort of had to put a red pen through a lot of the slides just to try and get things on schedule. So, what was our vision? Well, we decided we were going to be as ambitious as we could. We thought the whole thing of this was, let's not be incremental, let's look for big ideas, see where we can move forwards. It was our vision, or it is our vision, that we think within 30 years, variable speed drives will replace over 50% of all fixed speed motors. And by doing so, we think we're going to get increased functionality, increased system efficiency, not just the efficiency of the electrical side, but if you've got variable speed, there's so much more you can do in an overall system to improve the system efficiency. We think that they're going to dominate propulsion in automotive transport, which might be wrong, but we certainly think it's going to be a big player, and then there's nothing to suggest to me that that trend isn't going to continue to increase. And we think also they're going to just be increasingly integrated in everything we do. We hear so much about the Internet of Things. Maybe you ought to have the drives of things as well. There's so much happening there. I think there's going to be a very big influence. So we think if we're going to realize this vision, we're going to need some transformative research. And we think there are 2 really big things there. Can the overall system cost that we're working into be reduced? And can we increase power density and efficiency, making things smaller? In terms of how we do this, we think there's lots happening with new materials, new power devices, faster, more sophisticated electronic controllers, advanced design techniques are the things that we're trying to work together on collectively to see how we can move this forwards. So now you're going to see the objectives. If you don't think these objectives are ridiculously overambitious, then we've got it wrong, because we want to go that way. Let's really go for what we think we'd like to do. So what we're aspiring towards is, can we get a drive with a power density of 25 kilowatts per litre at 100 kilowatts? Now that would be a very strong, it is a very ambitious target, but we believe it is possible. Is it possible at half the cost of a commercial drive? Is it possible for a small drive to equal the cost of a universal motor so we can finally get rid of all these brush machines forever? Can we talk about quartering the system losses? Now, you'd say you're never going to quarter the loss in an electrical machine, but when that electrical machine is driving a fan or a pump, if the whole system losses can be reduced by a factor of 4 because of the fact we've got greater functionality and we got more variable speed. And can we increase the reliability by an order of magnitude so that we've got far more areas where we can introduce the drive? And finally, let's go for it. While we put all of those in, let's do it all at 300 degrees as well. So there are all the things that we're pushing towards. Can we get there? So in terms of what we're doing, we have 4 different work packages. We're trying, as we talked about before, at a less sophisticated level to integrate the motor and drive into a single package. We're looking at, as we're getting more wideband gap and very fast switching devices, what are the implications of that? What opportunities are going to arise for us? How can we get this reliability up? How can we understand more about the failure modes? How can we change construction methods or designs in order to get much higher availability? And how can we enhance the functionality in the operation of the drive? So those are our 4 themes. I'm not going to tell you which university worked on which, because we tended to all, different universities lead different packages, but we all work together quite a lot. So you're going to get it all in one bundle, as if we all did all of it together. So in terms of integrated drives, our aims were to use new materials and manufacturing techniques to get greater thermal, mechanical and electrical performance. This is what we put in our proposal. We aim to use wideband gap devices to reduce losses and harmonic distortion, and we aim to integrate the filter components into the package. And finally, we said we want to show this by creating a technology demonstrator at the end. So let me just go through a small amount of the work that's been done so you can see some of the things we did. So for example, we identified when we have an AC drive coming off the mains, there are enormous input filters, magnetic input filters. Can we integrate the filter in with the magnetics of the electrical machine? And there have been some work done in this in the past, but we came up with a lot of other concepts which hadn't been developed before. So if that's your initial machine with the main windings on, can we use, for example, the core back to create the filter? Or, another alternative, can we put another set of windings on the machine of a different pole number which create the filter? Or should we put the windings, we have another set of windings on the outside here to create the filter here instead? Or alternatively, do we put them in the core back? Now all of these are sized for a 3 kilowatt drive. These have all been done looking at a 3% per unit input filter, thinking of an LCL filter. And we looked at all of these things and thought, how do these all compare? And interestingly, it depends a lot upon the size of the motor, or the size of the drive. I'm alluding to exactly what John said earlier on. If you have a low-speed drive, the motor's a certain size, and it has a certain size of input filter, that's according to the power. If you make the motor go 10 times faster, it's the same size, the power's gone up by a factor of 10, and the energy storage on the input filter goes up by a factor of 10. And what we found interestingly was that in small machines, or small drives, low power drives, at low speed, we found it works best on the corners like this, and we're looking at ways in which we can integrate the filter into the corners of the machine. But at high speeds, it's better to actually integrate it more into the overall surrounding piece, and by having coils on the outside of the motor, sort of spread around, very much like the winding inductors. Other things we've done, we've been looking here very much at where should we put the devices. And of course, it depends to a large extent on the temperature of operation, whether we're using wide bandgap devices or not. So we've got things where we're putting the devices on the outside of the housing. We've got them here on the inside. We've got them here on the ends, or on the end plate here, or integrated more around the periphery. And we've been looking at this at different power levels, and we're coming to some conclusions about which way to go with that. Key to it, though, we find is really the thermal side. Getting an integrated drive is the key to getting high power density, is getting the heat out. So what we really need to do is minimize the thermal resistance between the sources of loss, whether they're in the power devices or in the machine, and the coolant. And when it comes down to it, it's mainly caused by voids. So either in the machine case, air between the coils we're winding, or the contact resistance between materials. And so we're doing lots of work trying to think how we can deal with this and get things better. So in terms of eliminating voids, just to state the obvious, you can impregnate the coils. So we're replacing the air here with a potting compound, and you can look at how much impregnation you have and how that affects the effectiveness. Or more controversially, what we're doing here is we're taking a coil, which you can see wrapped around a tooth here, and then we're pressing it at very high pressure and actually deforming the conductors. And you can see how the same coil after pressing is so much smaller. We got rid of nearly all the voids here, and then we build our machine up looking like that to get rid of the voids. And of course, there's all sorts of implications on the insulation there for us to think about. In terms of reducing the contact resistance between materials, well, we've done a lot of work where we've been taking a little dummy machine and we've been applying different pressures across the core back here, and we've been put it in here, and we've looked at the heat transfer and what we can do there and how it varies as we manage to get better contact. We've even looked at all sorts of things. Now this is getting perhaps into the silly mode, but it's still worth us thinking about. This here is the frame and this here is the machine. Now can we actually use friction welding? And the idea is, if I can get it to work, you spin the stator in here, and by friction weld the whole two come together, and you get a complete welded joint between the two, and that gives a very good thermal path. We've got someone who can do this, but unfortunately it's going to take a long time before we can get any results. If anyone's able to help us with that sort of testing, we'd be very grateful. So next steps for us on integrated drives, putting aside and integrating in with the work that we're going to do in this other project, which will supersede some of this, where obviously we're integrating the filter components. We're directly looking at, can we mount commercially packaged wide bandgap devices directly next to the coils. Let's look at this direct press on tooth windings, novel methods for metallurgical contacts as well. And finally, let's look at the possible increase in power densities based on the various types of power electronics integration we can get, and looking at direct die attach. And this will all come in, and we'll be using some of our resource here into the follow-on project we've got. So next work package, fast switching devices. We all know a lot about them, but do we know a lot about what it's going to mean when we put them in a motor drive package? So things we've been doing here, we're aiming to say, well, using these, can we improve our power density? Can we identify some optimal drive topologies? It may not just be a standard three-phase drive that we choose to go for. Can we understand what happens at high frequencies to the losses, particularly in the electrical machine and the iron losses of the machine, improve the system efficiency and performance? And let's try and build some prototypes to test this. So, in terms of what we've done so far, we've got 4 different configurations. There's a single standard converter, 2-level converter, or we can go to 2 parallel converters driving a double 3-phase machine, or we can put 2 converters in series, effectively splitting the DC link, or we can use what we regard as sometimes called an open-ended winding, where you effectively have a converter attached to each end of each phase of the winding. And both converters may not be wide bandgap width. Some might be standard silicon, one might be high switching frequency. So there's been a lot of design work done, and here you can see the CAD models, and here you can see the production. That almost looks too good. You've got to think we had the production, then drew that afterwards, haven't you? But I'll assume we didn't. And we look here at the efficiency of the system. When we're looking at different powers, we could get some very high efficiencies measured and predicted. We don't really always know a lot about what these high frequencies are going to do within the electrical machine. And so what we've got here is we have a number of different ways in which we can simulate it. So you can have a simulation model, and then the output from each time step goes into a finite element simulation transient, and then the output of the magnetics from that go back into the simulation model. So we've got a coupled model here, and then we get the losses out. Or we can have a simulation model in which we assume fixed parameters, and we put this into the finite element simulation to get the losses from that. Or we can have the whole lot integrated together, and we've looked at all these different possibilities. Now this is just a small example of what I mean about slides with lots of material on them. So I'm going to make it easy for you. What we've got here is we've got a MATLAB Simulink simulation. The output from that gives us obviously simulated waveforms, and then the output from that we can put into a static finite element simulation package. And from that we can predict our losses. So from that we can do it 2 ways. We can get analytical loss calculation, looking at the switching harmonics, and we can get simulated outputs that way, or we can do a full transient solution, and we're finding that actually some of these rather simple models are giving us pretty good comparisons compared to what we can get with transients. So the whole thing is here, can we produce some can we first of all understand the loss mechanisms? Can we also manage to predict them in a fairly fast way? So next steps on the fast switching side are to identify some novel switching drive topologies, as I've talked about here, to evaluate these and decide which one's going to be best. We're doing some experimental work to try and verify the predictive effects of these high switching frequencies on the electrical machine losses. Can we create a nice high frequency machine loss model without the need for using finite elements, so we can get something that works quickly in a system simulation, and to evaluate the efficiency of the complete system in one simple tool. So that's where we're going with these fast switching drives. Oh, and finally, to look at a dynamic switching frequency scheme for the overall efficiency. So if we put all of this together, how can we get the best possible thing out? So moving on now to our third work package, the third of four. This is looking at increasing the availability of machine drives. So this is something that is very much a cross-theme topic, because it's covering things, components from every, or parts of every theme. What we're looking here to do is to address really the key challenge. How can we get high reliability and keep high availability? So we're looking to increase the reliability by an order of magnitude, which is quite ambitious. Now, this doesn't just mean about producing fault tolerance. Fault tolerance might work in some applications, but in many cases it's just getting the whole system to be more reliable. And in doing so, we should open up lots of new markets for us in terms of where we can put the drive. So areas we're looking at, if you were to think about all the likelihoods of failures and all about fault tolerance, is we're not looking at these top three because these come under the other themes. What we're looking at here is the machine, the health monitoring and management, converter topologies, machines, fault detection and mitigation, and fault tolerant control. So to give you an idea of what we've managed so far, we've got insulation health monitoring, looking at the zero sequence, and I'll show you that in a little bit more detail. Looking at bearing health monitoring, and again I'll show you that. Reliability modelling and assessment of the fault tolerant drives, which ones are going to work out the best. Looking at producing a complete high fidelity electromagnetically coupled model of the complete system, so we can have active thermal management in there, which feeds into reliability. And looking at some form of model-based prognostic and active drive thermal management, and again I'll show you that in a minute. And finally, a novel machine type. So here's one example of what we're doing. We're looking here at a fast switching drive and looking at the current, the net, effectively it's the zero sequence current, or you could regard it as earth leakage current, coming from the three phases here, and we're looking at a low cost, very high bandwidth transducer here, and from that we're able to judge the quality of the insulation and see whether this is impacted as the life of the machine goes on. So there's one thing we're doing, looking at these leakage paths. The second thing we're trying to do on the model lifetime prognostics is, if we have some form of lifetime model of the machine in which you know about the machine's environment and operating conditions. So here we could look here, imagine this is the operating of the machine. You put this into a thermal model. That thermal model, through integrating out over time, talks you through the life of the system, and at the end we can come up with a prediction of the lifetime model. So we can try and judge from the history, the lifetime history of the drive, when things are coming towards the end of their life. Oh, another one. This was, I think, originally only a quarter of a slide, and I've managed to expand it to a full slide. Final thing we're looking at here is taking, effectively here we've got three machines we're putting into one to give us some fault tolerance. Classically, when you have a fault tolerant system, we tend to go for PM machines because they give us a nice high power density. But the problem is when you get faults, the currents continue to flow in the faults, and because of the permanent magnets. So what we're doing here is we're looking at a hybrid machine which has got a very high amount of reluctance torque, a small amount of permanent magnet material. It means that these fault currents can become very low. And this type of topology has been adopted a lot in the automotive sector, and we think it could work very well here as well. So in terms of next steps on the fault tolerance and reliability, we're continuing on with our health and bearing monitoring. We're looking at active thermal management, and we're looking at the fault tolerance system in this 3x3 systems. So there's 3 different strands to where we're going here. These top 2 are very much more about getting the reliability up and understanding the reliability. The bottom one about introducing redundancy. And then finally bringing us on to work package 4, enhanced functionality and operational management. This really has 2 rather different strands to it. At the top end here, we've got more about the operational management. So what we're looking at here is, can we have the machine and the drive working together to try and optimize them more at a system level? And there's 2 things, one where we have a single drive, and the other one where we have a system with multi-nodal drives. And then finally, at the bottom, we have one on enhanced functionality where we're trying to increase the temperature and see what happens there so we can open up new markets for the drive. Now, that looks an incredibly complicated slide. So what this is actually about is trying to create an environment where we can have a multi-physics model. So you can have all sorts of different simulation packages that all are working together. So our researchers work together, and I thought I'd just overlay that so you could see. So now we've created a system where we can have co-simulation between lots of different packages. So this includes Plex, MATLAB, Simulink, ANSYS, Excel, Simscape, AutoCAD, and Infinitiga Magnet. So we can easily move the parameters between the 2, and they can all become part of a big system model. And that's giving us an awful lot of advantages and helping us very, very much moving forward. In terms of single drive management, we're trying to make the converter and the machine more aware and responsive towards each other, trying to find the most efficient point for operation, continuously looking at the excitation pattern, the switching frequency, the DC link level where it can be modified. Actively managing the thermal state, trying to remove and anticipate and recover from the thermal transients, trying to reduce thermal cycling fatigue. Again, looking at lifetime prediction, feeding back into the other work package through online insulation measurement. And finally, EMI mitigation through switching frequency DC link modulation. On the multi-drive system, so here we've got a model of a single drive, but now we're feeding them into lots of drives, all feeding together here. There's 2 systems we can have. I'll just put the whole thing up, we can look at a multi-drive network where the drives are mechanically coupled together. And this could be, for example, where you've got a set of conveyor belts in a production system, or here where we're looking at more integration of open loop servo drives. In this top one, we're looking at efficiency. In this one, we're looking more at the component rating. So coming to the other end, I mentioned to you before about high temperature. So we've been doing a lot of work looking at increasing the ambient temperature. If we've got 100 degrees C ambient, it's great for vehicle systems. 200 we can get into oil, gas compressors, pumps, etc. 300 would be very useful for aerospace. Now there's an awful lot being done on insulation and creating high wire temperature coils, capacitors and switches. What we've been doing is taking a lot of systems and also measuring them to see how they perform. So this is you might regard it rather naff slide. This is a before and after, and the after doesn't look too good this time. It was running at 500 degrees. So we've created a system where we have been putting a constant amount of tension around a wire like this, running it at different thermal environments. We've been using copper and aluminium, and here we've got some ultrasonic welding for the aluminium onto its contacts. And then we've been looking, now this is rather difficult for you to see, this is the resistance as a function, resistance to earth as a function of temperature, and these are for all different wire characteristics, and you see we've got some here that we're able to operate over 500 degrees, and some which are failing at not much more than 200. But we are having quite a bit of success here looking at different systems. Next steps for this this package, well, let's look more on the single drive management, demonstrating real-time operating point tracking, looking at fast temperature observers, insulation degradation, multinodal model. Let's create more of a system model than we have at the moment, looking at the different efficiency trade-offs and validating it. And then finally, this high temperature work. We're building test coils and we're integrating temperature sensing here. So here there's an optical fiber, 1/4 millimeter diameter, that we're using embedded in the coils to look at the temperature of the coil. Also looking at inductors and capacitors and high temperature drive demonstrators. So you'll see there's a huge breadth of work going on across the 5 universities, and it's all coming together I think it's coming together very well. We certainly have, we're talking monthly, and we're meeting face to face every 3 months, and I have to admit, I feel very positive about it. I'm sure there's lots of things we're doing in there you might find controversial or disagree with, but we all think that we're doing some good work. So thank you.